All right, thank you. All right, everyone, how are you doing? Good is good. Do you have the notebooks up? Yes, everyone all set? You're all in your little groups, okay. So, all right. The references, again, but let's do a recap. Where was my magic eraser? Who had it last? Oh, did you reconfigure? No, you sort of stayed in the same place. It's good. Who had the magic eraser? Oh, I found it. Don't worry. I got it. Oh, yeah. Okay, who had the last question? I don't think so. Did you answer any questions yesterday? All right, we're starting from here. Okay, so what did we talk about yesterday? Can you tell me what's an asymmetry? No, the eraser.
Oh,
It's on the slide right here. You don't need to look at anything else. What's an asymmetry?
asymmetry is, I mean, it's on the slide.
Yeah, but explain it to me like I don't know it.
Yeah, so you have like two different like measurements. You could have polarized or unpolarized, for example, and then the formula is given over.
Yes, exactly. So you have two different conditions, and you can take the difference between your counting rates and you divide it by the sum, and that's your asymmetry. And so now you can pass it on because we're doing a quick recap here. So at the EIC, no, I see you. At the EIC, what's the condition that we generally sort of flip around? What's the experimental condition? What creates two different conditions here?
The polarization.
Yes, exactly. See, it's not, they're not tricky questions. They're all fine. Yeah, the polarization of the electron or the hadron, or both, actually. Because you can have single spin asymmetries when only one of them is polarized, or double spin asymmetries. So how do you can pass that on. So how do you, if you have two things that are polarized, but I'm only interested in the electron polarization or the asymmetry from the electron polarization, what do I do with the hadron polarization? Can I make a measurement if the hadron's polarized? What do you think?
Well, we talked yesterday about Compton scattering. If you want to,
Sure. We'll get to that in a minute. But this is just a separate question. So I have an electron that's polarized, hadrons that are polarized, so their spins are separated, are flipping around, right? But I'm interested in a single spin asymmetry, meaning I only care when the electron flips polarization. Can I make a measurement if the hadron's polarized, or is that gonna, because the hadron's polarized, is that gonna screw up my measurement? What do you think? I don't think we didn't discuss it yesterday, so it's a brand new question, spanking brand new.
I think so. And then you could average over your hadron.
Bingo. All right, exactly. That's exactly right. So you can average over one of them. You can sum up the different polarizations for the hadrons, and that will get you an average, or zero polarization for the hadrons, and then you can have your electron polarization. All right. So then we talked about the electron, the amount of polarization for your electron scales your measured quantity in order for you to get your physics asymmetry. So what did we, oh, we can pass that on, right? Okay, already did, great. So what did we say in order to measure the polarization, what do we need? Do you remember? Do you wanna ask a friend? Yes. Anybody else? What do we need if we want to measure up the polarization of the beam? That's something that's sort of an experimental thing, but in general, if I want to know the polarization of a beam and what is it that is prerequisite? I need to be able to, in order to measure it, I need to have what?
You need to have one asymmetry you know really well.
There we go, right? So this is my analyzing power. This is the one thing we have to have a physics process that's been measured so well or calculated extremely well that I already know. And what was that physics process? Do you remember what we were talking about yesterday? You know the Feynman diagram there? Yes, excellent. So that's Compton scattering, right? You can pass that on. So why is Compton scattering useful here?
Should scatter off.
That's excellent. That's a great point. Experimentally, when I put a photon and there's a bunch of electrons around, I scatter off the one electron and the rest just go on their merry way. That's an excellent experimental point. But in terms of in the context of a polarimetry measurement with an analyzing power, what makes a Compton scattering useful? What kind of process is it? Well, it is. That is correct. That's a good point. But is it QCD? It's a QCD process. Yes. And what do we know about QED? Yes, we do. Excellent. All right. So we know a lot about QED. So this means my analyzing power, I can calculate really well, right? So now if I do this experiment and I measure if this value is 30% of this value, you can pass that along. What's my polarization? Exactly. So it means that I know that in my physics process, I should get a 5% analyzing power, but this is 1.5%. Then it means my polarized beam was only 30% polarized. All right. And we sort of ended yesterday where we calculated. So we had this gamma factor. Apologize for the typo yesterday, but this is this gamma factor for an electron beam where we have the electron beam energy divided by the mass of the electron. And we can calculate the scattered photon energy based on the scattering angle and the energy of the laser. Do you remember for a 532 nanometer laser, what sort of energy we're talking about? Yeah, exactly. Yeah. Anyway, that's a good answer, but I'll get to you back. So it's 2.31. Oh, now you answered. Now you have to tell me what? 2.3 what? EVs, that's right. EVs are compared to GeV much smaller. So this thing goes way back, right? So it's a back scattered photon. That's the important part. Now, looking at this equation here, who has the magic eraser? All right, looking at this equation here, when do I get my maximum photon energy? Exactly. If I make theta equal to 0 in terms of scattering angle, I get this maximum electron energy, and we calculated that, or you calculated that. And for a 1 GeV beam, which is not going to be at the EIC, you get a maximum photon energy of 34.5. For 11 GeV, you get 3 GeV, right? Your maximum photon energy. All righty. Yep.
Beam, what is the range of energies for an electron beam at the EIC?
So 5 GeV to 18 GeV. Yep. All right. So, okay. Actually, before we go into this, so what happens? So this is the maximum energy. You can pass it along. So now we have the maximum energy. What do you think what's the distribution of the photons going to be? Do you have a guess? Sorry, I couldn't hear you. Oh, you weren't here yesterday. It's okay. So, all right. So that's perfectly fine. So we have this equation here. We'll figure it out together. So we have this equation here. That's the energy of the photon, and this is the scattering angle here, right? So he just said that if this is 0, this is maximum, right? So at 0 energy, when the electron comes in, hits the photon, and the photon doesn't have any scattering angle, just goes straight back, we have maximum photon energy. But if it goes slightly up, it's going to have less energy, right? Does that make sense? So the distribution of this, it was a sort of a trick question. I don't actually expect you to know what a Compton spectrum looks like, but this is the distribution. So this is what's called the Compton edge. This is your maximum energy, and this is the distribution of rate. So this is, you can think about it. This is energy on the x-axis, and this is just sort of a histogram of how many events I get at different energies. So you can see I get sort of this particular shape, and that's what's called the Compton spectrum. All righty. Okay, so yesterday homework. Let's see who did their homework. We discussed about calculate the angle for which the scattering photon energy is half of the maximum energy. Right? So I think I gave you a little equation yesterday. I don't have it on this slide. I did, right? So did anyone look into that? Did they confirm that it sort of makes sense? Yes? Okay. All right. So we'll start off from here. So if I want to look at the half of the maximum energy, right? So we have the spectrum here, and I want to know, like, if I look at this energy spectrum and I say, well, at about half the energy, what's the scattering angle at which this photon goes, right? So then I can calculate it, and this is in degrees. This is 0.006 degrees. So you can pass the thingy along. So how large of an angle is that? Okay. So this is, if I calculate what the angle is for half of the photon energy, I get this number, 0.006 degrees. How large of an angle is that?
90 degrees.
No, so we said that for maximum energy, I have it, I think basically zero, going very, very backwards. And for half of that energy, it's this number, right? So it's 6 millidegrees. So do you have a feeling for how big that is?
Very small.
Very small, exactly. So, well, no, go away. All right. So now, first exercise of the day is, so what I wanted to point out is exactly as you said, it's a small degree, small angle. So if I want to be able to measure that photon out of the electron beam, because the electron beam is going straight, right? I have to measure it away from the electron beam. So in order for me to get away from the electron beam, I have to have a very large distance. So I want you to take this angle and calculate what the radial position for this photon is after 30 meters. So that's your first exercise of the day. Go. I don't remember, sorry. For 5 GV, you said?
Yeah.
I assume that's 30.
757. Yeah, that's what I remember that. Because that's 757 MEV. Yep.
And if that's the case, I'm not getting your 0.006 degrees. I'm getting.
I think
Wait.
gamma squared goes into
So
that's weird. My mom's.
This is in degrees, but tan is radians.
No, it should save automatically.
Yes.
Exactly.
Double check on that.
We're multiplying by gamma, there should be in the denominator too.
All right, I hear one good answer. All right.
Why for you sending me this?
I don't know. We'll look at it. Anyway, you got something. Good? Yeah, it should be. Yesterday we had 5,000. Yeah.
Yeah.
You have a problem.
I
No
didn't
problem.
get the right
So,
one.
you're gonna want to you multiply by 109.
I will come as an actual solution. So you can actually.
Yes.
Yeah, right. I don't want to waste your time. All right?
Yeah, sure.
Oh.
Yeah, what is it?
Theta is gonna be relative to the scattered electron count.
Yeah. I think it's actually, I think we're good.
All right, we good?
Yes.
We have some idea what we're doing? How would we do this? Who has the magic eraser? All right, how would you do the calculation?
Well, as you pointed out, the angle is very small, so you can just approximate the theta with theta, and divide out the radians times the 30-meter distance.
That would definitely work. You can make a small angle approximation. Alternatively, you can do the tan if you want to be super stickler. And you get, I get 0.3 centimeters. So after 30 meters of travel, so if I have my Compton scattering here, 30 meters is way that way. I'm gonna get just 3 millimeters off the beam line. Okay. All right, so let's move on. So the next exercise is looking at the cross section. So what's important? Why is the cross section important? I mean, there's a physics process. Why is the cross section important? What does it tell us?
How likely?
Yes, exactly. So it'll tell me how, if I have a bunch of photons coming this way, a bunch of electrons coming that way, how often will I get that? And why is that important?
Very important.
Sure, it is. I mean, in general, it's nice to know, but as an experimentalist that wants to measure electron beam polarization, why would I care?
So close because.
This is how likely you are to get a constant.
Yeah, yep.
Well, if you're not measuring what you expect.
Just hands.
Yep.
Then
Oh, so yeah, if I would be measuring rates, but I'm measuring I'm measuring asymmetry, right? Which, rates are in there. But say this comes out, the rate of this is once a week. Is that gonna be good? Why?
because we need to know what the polarization is more often.
Yes, that's exactly right. We need to know polarization on a very fast pace, right? We can pass it along. Do you remember how you had an accelerator talk, right?
Yeah.
Okay, so how often at 18 GeV are the electron bunches gonna be replaced?
How often are they going to be replaced? Isn't it like once every minute?
Good order of magnitude, about every 6 minutes or 4 or 6 minutes, something like that. So that's a good memory. So it means that if I want to know what the polarization of that bunch is, I have to make the measurement in
Like now. You
like
gotta do
now, less than that, right? Less than that. And this is part of the exercise that we're going to do today. All right. So next exercise is calculate the cross section. So this is the unpolarized cross section. In the Jupyter notebook, you have some constants. You've calculated rho and A from before. Actually, rho is a parameter because I want you to look at the cross section as a function of scattered photon energy. So code that up real quick so we can look at the unpolarized cross section. Correct. You use the A from before. The A was you already calculated earlier or yesterday.
Wait, you meant it. I did. Oh yeah, man, I'm good. I'll do pi to all digits.
You go that twice?
Like the percentage of the energy you inject into the maximum. So you say rho 1/2 means half of the maximum energy, and you want the cross section for that particular energy. Probably see if you still have the old one. That's how I understand. But it's defined this clears me. Froze input argument.
Anna,
So-
you have A from yesterday, so I can confirm my A is correct. Okay,
A is here.
no, but like a number, so I can confirm my numbers.
A depends on the energy of your laser, which is 500. We discussed 532 nanometers. Yeah, I don't know what A is actually the number.
Guys, what is A for 532 nanometers?
We solved it earlier in the code.
Yeah, so can you say what it is?
I got 0.8485 something.
Yeah, 0.8485. My bad.
Thank you. All right. How are we looking?
Yeah.
Did anyone actually get this number here for a cross section for half the energy?
Something slightly different
Slightly, how slightly?
on the first digit after the point.
Let's see, what is that? That's like 20% different?
Yeah.
Experimentally speaking, we're probably all right. Okay, all right, I'll take that. Anybody else? Yep. Your function that you're going to find, it's the input. Could be 0.5 in this case. So for example, so, all right, just sorry, I didn't explain this, but my hope here is that you'll create something called Compton_exsec as a function that takes in an input, and that input will be rho. Right, so that you can calculate Compton cross section of 0.5, 1, 0.2, whatever you want, right?
How did you go? I can stay. Yeah.
You got your number because I was.
When we calculate tan of angle, what
Oh, you get the same.
our theta should be in radian or in degree?
Gets 0.3.
But I mean, for the previous exercise, what did you get? He said you could take a small angle approximation.
For the angle.
Approximate with the angle.
Oh, for the angle. Or after turning it to degrees.
Like as a fraction. Oh, no, I mean the radius. So
Oh, the radius.
0.0.
Yeah, I got that in yours.
For the tangent, if we should put it on degrees.
So you already put the turn state.
I think it was just tangent because it's such a small angle, it's approximately. As long as you have it.
I think you have to be careful. Yeah.
1 over gamma
Would,
That's what I have there. Square root of 1 over gamma
Is radians.
or 1 over square root of 8.
But I have my data half defined radians, so
okay.
if you just, yeah, if you just do 30 times your angle and radians. You get your sort of radius.
Oh, 11 GV. All right. So that's for a half GV. My results are for half GV.
Oh, okay, then,
You're probably.
okay, I will double check just that numbers. Okay, good.
Maybe you just put the angle.
All right. How we doing?
I got a wrong answer. I'm trying.
You got a wrong answer. Okay, good. You got a wrong answer too? So this is for 5 GV. Okay. All right. Let me look at it.
Does A depend on the angle?
No.
Yes.
Yes.
I understand.
Or that.
Please see what you wrote. Please see what you wrote.
Did I, was it not on there? Sorry, that one.
Thank you.
Sorry.
That one.
Because we need to
You don't have to, it'll, you know, minus 24. So that's centimeters squared, so it's. That's
And then
half-
there,
half-
that's your
half
variable.
a bar.
And then I define it as like the function.
It's perfectly fine, it's half a
As
bar.
long as you have the return, yeah,
Yeah, that's, good question.
Yep. yeah, yeah, everything indented because Python is indentation. Or it cares about white space.
No, I'm.
But yeah. Except the typing here. Big nasty.
Square on. That's a good question. So I'm not touching on that, but yes, it does have to be polarized because it allows you. And then you can measure. I'm just. Bunch. The other thing you do is you have your. Higher. Change of polarization.
Might be better than others, so.
Yes, between that. Yes.
Subscriptions.
I'm not running.
Yes, so that you could get things between if your electrons polarized, or if your photons polarized. And minus 25?
Yeah.
Okay, so you're in the ballpark. Ballpark is all I'm looking for. I'm an experimentalist.
I think all of us get
Yeah.
4.5.
Okay, so maybe mine is wrong. I see what you're saying there. Okay, it could be.
Maybe your two is just upside down.
Good?
That's a 5, right?
Getting that.
Yes, no, maybe?
Yeah.
I'm not getting it, so.
So close.
All right. I'll give you 30 more seconds, then we'll move on.
Half energy, 4.5.
Code review.
Code review, yeah, well, when water comes around, we'll ask him for a code review, yeah? Okay, good.
See, there's a, between the two directions,
There's a 1.
Thank you.
What's this?
Yeah, nice.
Nice, yeah.
Oh,
All right. So now, if you use that function and you go to the next cell, you'll make a plot. And the plot should look something like this. So the x-axis is rho. Who has the magic eraser? What's rho?
So is the energy difference from the, basically the energy of the scattered photon
Yeah.
divided by, so it's the difference between the scattered energy photon from the maximum.
Yes, that's perfect. It's exactly right. So it's energy of the photon that you're looking at divided by the maximum photon energy. So if I'm looking at the unpolarized, this is the unpolarized cross section. I see this sort of U shape here with the lowest probability or cross section at about half. And at 1 and at close to 0, I have the highest probability. Okay? Did whoever finished the function, did you manage to get a similar plot? It's a little bit crooked. Okay, all right. Well, I'll just for everyone's sake, I will post solutions, and you know you can look through it, and maybe I made a mistake, and you can point that out to me. All right. Okay. So now the next thing. So now we know we have the unpolarized cross section. Actually,
That will go a different way.
that was a good question. What units are these?
Centimeters squared.
Centimeter squared, exactly. And does anyone know who has the magic eraser? Do you know the conversion between centimeter squared and bar? No, okay. All right, that's fine. That's a good, honesty. Anyone knows? Oh, no, just go back. Do you need to answer something positively?
That's the one minus three.
Yes. Did everyone hear that?
1 times 10 to the minus 24th cm squared.
Okay, thank you. All right. All right, so now that we have the unpolarized cross section, we can look at analyzing powers. So these are, again, it's a QED process, well known. Again, I want you to calculate define a function that looks something like this. And this is the equation for it. This is the unpolarized cross section, same constants you've been using before. That's the previous function.
Nine, this one, yes, why not?
It'll be a positive function. Because I have
Sure.
to do next.
You can call a function another function. That's fine.
Yeah. What? You sure about it?
Yes, or else it will try and call rho as a function.
The cross section is consistent with 0.
एक मिनट दिखा गलत है
Thanks, I appreciate that. Yeah.
हमारी स्क्वायर
I mean, if you had a similar value before, you'll get a similar value now.
You're doing now.
How do you mean? You mean
Next.
Again, this is a homework exercise.
All right, never mind. Yes.
There's one more next. Next.
What do you have? 199.
Yeah.
Yes.
You get 119?
Yeah.
Negative, yeah.
What is this? Oh, good question. What's the analyzing power? Damn it. There you go. You got stuck with it. What's the analyzing power? What are we looking at here? Yeah, obviously.
What is the analyzing power?
Yeah. Remember what we were talking about at the beginning? If we want to make a polarization measurement, we want to know what? I know the process very well, yes?
Yeah.
So the analyzing power is the asymmetry that was.
Symmetry of the incoming beam.
So of the process, right? So the process itself, this QED process has an asymmetry, an intrinsic asymmetry.
I always forget that.
Yeah. If I measure that, if I measure this process, then, and I get a smaller asymmetry, then it means my beam was not fully polarized. And that's how I'm getting my polarization value, right? So the analyzing power is the physics asymmetry for this, right? It's the analyzing is the asymmetry that this process has. All right. Does that make sense? Did I answer your question? Or did he answer your question? Does it make sense to you?
But you're not measuring, like, I thought this symmetry was
This is a,
between the
this is a
thing
calculation.
measured and the thing that you know is gonna be, if it's fully polarized.
So this is the asymmetry of this process that someone calculated and got this analytical equation,
Okay.
right? So whenever I have this process, if my electron or laser or both are polarized, I'm gonna get this analyzing power, this asymmetry. Okay,
That's the symmetry that we know.
we know this is God-given or whatever you want, whatever deity you want. That's what this is. That's what you're calculating.
Okay.
All right.
You really want to maximize your analyzing power, so you want to choose the process.
Exactly. So that's a very good point. So actually, let's chat a little bit about that. So why do you want to analyze? Why do you want to maximize your analyzing power?
Because you're not going to have full polarization in the beam, and you want to maximize. I mean, you're looking for polarization measurements. You want your beam to be up at 100%. You want to get as much polarization as you possibly can. Am I saying it right?
Yes. Does that make sense? So another way to point this out is that if I have a large analyzing power, then the difference between one helicity state and another helicity state will be big. So I know if my electrons are pointing that way, I'm going to get 10 events. If my electron pointing this way, I'm going to get no events. So I have I have a maximum analyzing power. Does that make sense? Okay. All right. So in the interest of time, because I want to talk to you guys about some other stuff too. This is, once you calculate the function, this is what the longitudinal asymmetry or analyzing power looks like as a function of rho. So you can pass on the magic eraser. What am I seeing in this plot? Crosses zero. So what does it mean? If I measure a photon that's 0.3, so I have a magical way of only selecting the 0.3 gamma or rho photons. What asymmetry am I going to get? Correct. And if I do 0.9, right. So now if you can pass it along because that was a good solid answer. So now if I actually manage to make a measurement as a function of energy of the photon, I'm going to get this shape, right? Does that make sense?
Yeah.
Yes. All right. So no, you're still there. So can you think of a good reason why this type of shape would be interesting for an experimentalist?
Measuring something negative versus measuring something that's positive is easy to do.
Yeah, so having a shape that does this is very nice. Where are you sitting here? So at this point, one, what is one?
What is rho of one? So the max energy equals the energy.
Correct. So this is the maximum photon energy, which we can calculate. So we know what the maximum photon energy. So I know the end point, right? Now, if I can measure what this point is, now I have another point. So now I know my maximum and I have another point. This means that I can, in a detector that I have completely no calibration for, I know what I found. What did I find out here? Exactly. So you can draw a line and you can basically figure out what your energy calibration is without having a really fancy detector. Yes.
I think I'm not an experimentalist because I said, okay, I want to maximize a longitudinal, so I'm going to go and take one measurement sitting out there. One good.
Yes, that's a good point. But because we have a rate, this rate is much smaller than the entire thing. So there's some downsides. All right. So okay, you're next.
Oh, yes.
It's okay. It's all right. We'll walk through it. All right. So the next exercise that I'll leave for you as a homework is to look at the transverse analyzing power. So what do you think the transverse analyzing power means?
Polarized, so we have 90 degrees between them.
Yes, exactly right. So if my electron's doing this and we're scattering off the photon that's longitudinally polarized, I'm gonna have a transverse analyzing power. And in this one, how was the electron configuration? It's longitudinal.
But we have to transfer.
No,
This is for longitude,
which means what? How is the electron compared to the photon polarization?
90 degrees.
That was transverse,
Yes.
and this one is longitudinal, so along the same axis, right? Yes, yeah, exactly right. So now we have we have a transverse analyzing power. So if my electron polarization is this, and I have a longitudinal analyzing power. And so this means that if I have my electron doing this, can I make a measurement? Go ahead, reason through it.
Some scattering, yep. And it depends what you would like to measure.
Sure, but the polarization of the electron beam. So I want to know, so we said, if I have a transverse analyzing power, I have an analyzing power here, right? So I know what should come up. If I have a longitudinal, we did that on the previous slide, but now it's at a weird angle, just a random angle, because sometimes I can't control it properly. Can I make this measurement, you think?
Yeah.
Why?
Because you have longitudinal and transverse.
Exactly right.
And compute, for example, the cosinus from this angle.
So did everyone hear that? Yes, no? So if I am sitting at a weird angle, because I have a transverse analyzing power and I have a longitudinal analyzing power, I can decompose this into what?
Two variables.
Longitudinal polarization, transverse polarization. I can make these two separate measurements and I can determine the polarization at any angle that I want. Does that make sense?
Yeah.
Okay, excellent. All right, so if I look at the analyzing power here as a function of rho again, but notice that one important thing is that this has a cos phi component. You can pass that along if you want, or you can keep it. You and I can talk for the rest of the day. It's up to you. So what does it mean that it has a cos phi component?
This is for our in 2 dimension, we take into consideration all phase space, 2p.
Exactly. So it means actually that in 2 pi, it'll be different. The analyzing power will be different. So this is at phi equals 0. So it's basically in the same direction as the electron spin. And you can see that, for example, this one doesn't have a nice node at 0, so I can't do my fancy energy calibration here. But I think, let's see. Okay, so we'll talk about this in a little bit more later. So, all right, let's pass this along. Thank you very much. All right. So, okay, let's discuss a little bit. So now we've talked about analyzing powers. We've talked about photons theoretically interacting with some electrons, but let's try to get to some actual experiments. We talked about the photons coming in as a laser, right? How would I have the laser interact with the electron practically? How do you think? How would we do this?
How we have the laser interact with the electron?
So, okay, let me rephrase that because it's probably, so I have a beam pipe. And my electrons are coming in this way.
Yes.
Yeah? How do I make them interact with some photons?
You have a laser beam coming in the other direction.
Okay, where?
From this way?
All right, so I'm putting a laser beam this way.
Yes.
Okay, so this is my laser beam box. Okay, so what happens to all the electrons that don't interact with the photon?
What happens to all the electrons that don't interact with the photon? They go on by.
I mean,
okay.
The box is here.
Oh, okay. Well, they're gonna do some damage to the box.
They're gonna do some damage.
Okay, so what we need to do then is we need to put yeah, okay, so we need to put the box at an angle then.
Yes, put the box at an angle. Perfect. I like it. All right. Box comes in at an angle. So now that we have an angle, Let's talk about the electron beam. How does the, oh, you can pass it on. That was great. Thanks.
Okay.
So how does the, so we have electron beam. What is the electron beam?
Electrons.
Sure. They come in, you've had the accelerator talk, they come in what?
In bunches.
Yes, bunches. Okay.
Thanks.
I'm
sorry.
How would you imagine a bunch looks like? How are the electrons in a bunch? Are they, like if the bunch goes this way, are they sitting like this and they're all doing that? Or are they lined up one after another like this? What would you say?
Probably a action of some sort, and there's momentum
Yep,
difference. And
that's perfect. So it's sort of a three-dimensional Gaussian, in fact, four-dimensional because you have energy spread as well. So we have, let's imagine a blob of electrons coming in, right? So we have more electrons here, less electrons there. And now the photon, the laser beam comes in fairly similar, right? Now, if I did the original suggestion of putting the box here, my blobs here, what would be the overlap for them?
the original, like,
Yeah, let's assume I can imagine put the box here and
to get full overlap.
yes, I can get full overlap and that gives me what?
Yes.
Well, I mean, the laser box dies, but yes, I do get the highest possible rate, right? I have the maximum overlap, so I can get the most amount of scattered particles. Now, if I'm at an angle, what do you expect that will be more, less?
Some points have full overlap.
Exactly. So, right, so the luminosity will go down. So the bigger the angle, the lower the luminosity, all right? Okay. So let me, where's my thing? Jeez. Here, got it. All right, so let's talk a little bit about one of the implementations. So this is I hate this. So this is the design area for Hera. This is the beam pipe, and this is exactly what you pointed out. The laser, I mean, I don't have the laser box here, but I have a mirror, which is good enough, comes in at an angle. And the angle that they managed to do is, I think, 3 milliradians. So notice that in this region here, this is 42 meters. So these things are spread out very large in order for me to get the smallest angle, because that gives me what? Correct. That gives me the highest luminosity. All right. You can pass it along if you want. All right. So that talks about okay. So let's talk about luminosity. Let's pass that along. So we discussed about these blobs here. What would you imagine? What are the parameters of these blobs that you think are important for my luminosity, for my rate?
Sorry.
So these blobs, I can parameterize them by some parameters, right? Like the width of the blobs, the length of the blobs, the angle between the blobs. What are some of the parameters that you think are going to be very important for my luminosity?
I mean, it's the angle of the blobs coming in.
Yep, the angle. So we discussed this. The angle, I want to minimize the angle. Anything else that comes to mind?
Yes.
So the polarization is sort of a property of each individual electron, and we can talk about the entire bunch. But imagine this configuration versus this configuration. Which one would give me a better rate, a higher luminosity? This one, right? So my transverse width here is going to be important, right? Also, if I'm having this at an angle, how about the longitudinal width?
It's also important if it's too long. Having so if you have too much of a longitudinal width, then the amount of photons are not going to hit.
Exactly.
Enough
All right.
electrons.
Perfect. All right. So that's exactly right. So if I have another homework item for you will be to calculate and implement these luminosity calculations. And do you know what kind of lasers people produce?
I think I do.
Yeah, tell us.
RF lasers.
Sure, what kind of, an RF laser is the type of laser, which,
CWB.
what is CW?
Continuous wave.
Okay, so what does that mean to you? How are the photons coming in,
Well,
roughly?
roughly like a pulse wave.
Yeah, so a continuous wave, a continuous CW laser, you can think about it as literally a beam that it continuously comes in, right? So now if I have, and then you mentioned RF, where now I have blobs, which is what I pointed out here, right? So they're coming in at blobs. Yes, and they have an associated frequency when they're coming in, right? So if I have the same amount of power in this beam, and you can pass that along, in this beam and that beam, how the number of photons per, let's say, unit time here, where is it going to be higher? I have the same amount of power.
Yeah, in the bottom one then, because you're punching this together, right?
Yes. So if I'm taking the same amount of power means the same total amount of number of photons I have, right? So now if I'm taking some of these photons and squishing them here, then it means they're more concentrated in the pulsed wave. So the luminosity equations here, they're going to depend on if you have a CW laser or a pulsed laser. And the pulsed laser here will depend on the frequency of the collisions, number of photons you have in your bunch, obviously, like the number of electrons you have in your bunch. This is the scattering angle that we saw, the width that we talked, the transverse in X and Y widths, and again, the angle and the longitudinal width. All right. Does that make sense? Yep.
For why longitudinal width shouldn't be so big? Why?
So, okay, sorry. Imagine if I have 100 photons and I've put them here, but if I space them out within a meter, if my electron beam passes by, which one am I going to have a higher percentage of higher probability of interacting? The small one, right? So if I squish my electrons in a small bunch, my photons or my electrons in a small bunch, that's why this is important. So this is the longitudinal width of the photon and the electron. Yeah. So if I plot this as a function of crossing angle, so this is the angle that we talked about. This is the luminosity in centimeters square second. This is an RF pulsed laser. So you can see the luminosity drops off. I mean, this is a linear axis, so you can see it drops off a little bit. So as we talked about, larger the angle, lower the luminosity. But if you have a CW laser where it comes in just as a beam, it drops off much more drastically. So if you want to have a high rate, you would go with a pulse laser. All right, what am I doing now? Okay, so last thing we're calculating today, the photon rates. Let's calculate the rate of scattered photons for a single bunch collision, assuming this rho min is E laser over E gamma max. So this is what you have in your Jupyter notebook, I think. I've updated it this morning. So the luminosity for one bunch is this number. So I calculated for you. The collision frequency is this number. This is rho min, and this is a sort of an integration. So this does the integration of the content cross section from rho min to this value. Let's see. And the question is to calculate the rate. How would we calculate the rate here? Oh, actually, who has the thing? Let's go through it. You want to pass it along or? Okay. All right. So this is my luminosity equation. How would I calculate the rate here?
The rate seems to me it's just this dN over dt. So I rearrange the equation.
Yes. All right.
So it's luminosity times cross section.
Correct. So now I have my integrated cross section here. I have my luminosity. What do I have to? So I have the luminosity for one bunch. If I want to know, what do the bunches do at the EIC? What the electron bunches do at the EIC in the collider? Sure. And then after they do one interaction, what happens to them?
Or they go around and then they interact again later.
Aha. And what do you know what the frequency of that interaction is?
Well, it would be like the length of the accelerator divided by the speed of.
Look at that. That's a good, yeah, 78 kilohertz roughly. But that was a great answer. I love it. So actually what you can calculate, you'll get a backscattered photon rate of 58 kilohertz. So per second, I get 58,000 events. Yes, we're skipping the luminosity. I'll leave that as a homework. Yeah. So as you pointed out, this would be the cross section times the luminosity of one bunch and the frequency at which that bunch comes along, right? And I get 58 kilohertz. So now the last thing I need to do is I need to convert this somehow into amount of time it takes me to make a measure. Yeah, does that make sense? So you can pass it along. So I'm not gonna walk you through the derivation, but this is the equation to determine how long it'll take me. So this is the time, it's the inverse. So this is the luminosity times the cross section. The polarization, what's dP over P here?
That's the relative uncertainty of our polarization.
Right, exactly. So in this case, what I would do is if I wanted a 1% measurement, I would put 1% here, right? And then this A method squared. So now we were just talking about earlier that I get 58,000 interactions per second. Yeah. So when I do that, how would you, what could you do with those photons? How would you, do you know how, what kind of measurements could you do to those photons? What do you think? Just go for it. Doesn't matter.
Oh, count them.
Yes, that's a great point. We can count them. We were trying to measure them as a function of what earlier? What was rho?
That was like the energy divided by the maximum energy.
Right. So if I manage to make a measurement of the energy, do you think that would be useful?
Yes.
All right. So what do we measure energy with?
Calorimeters.
Bam. All right. So we have a calorimeter. So we can measure them. Now, you have detector talks. Let's see how well those go. How fast do you think our kind of calorimeter measurements going to be able to measure? So if I have 50,000 of them coming per second, am I going to measure them one by one? Can I do that?
I have to kind of bunch them.
Yes, exactly. Right. So there's a time. So photon comes in, interacts with the calorimeter. It takes a bunch of time for the energy to come out and for the material to go back to its ground state to be able to interact again. So there's different types of measurements that we can make. So the first one is when we can make an average, right? So I take exactly as you said, I take a bunch of photons and I just do the average. So in this case, remember that analyzing power that we had as a function of energy, I'm sort of averaging that out, right? So instead of actually getting a nifty one value of energy here, one value of energy there, I'm actually getting an average, but you could still make a measurement for that. Okay, that's one. Then you can have a energy weighted measurement where not only you count them, but you take the energy of those combined, of the energy of the photons combined. And then you can have a differential measurement where instead of 58,000, maybe I'll reduce the rate to maybe 1,000 or something. And then I can measure them one by one. So a photon comes in, oh, this is one GeV photon, oh, 500 MeV photon, and so on and so forth. Yeah. So this method here is the analyzing power for each of these. And you can see that this where you integrate, this has the smallest effective analyzing power. If I consider the energy, I have a larger analyzing power. And finally, if I do the differential measurement, I have a slightly higher analyzing power. You can pass that along. Why do you think that is?
Analyze each one of them.
Okay,
So you're gonna,
so you're gonna get what?
very precise.
Yeah, so you're gonna get more information, right? As I'm going from here to there, I'm getting more and more information. So each measurement is gonna be easier to make. All right, so again, this is an exercise that you can do, and I'll leave that for you later. If we look at differential measurements, so you can see here, I have a table of different measurements, and this one is in seconds. So this integrating method gives me like 29 seconds to get to 1 precision. This differential measurements gives me milliseconds, so I can get to 1% in milliseconds. And finally, this energy weighted one gives me, again, milliseconds. So I can get to 1% precision statistically very fast with this method. If I have time, we'll talk about this later. How can we make this measurement? All right, last thing we'll discuss. You can pass that on to somebody in the back. So I have my bunch coming in here, my bunch coming there, and I have a backscattered photon and a backscattered electron. This is a wiggly photon. And I have my electron beam coming this way. How would I be able to separate these? So first off, I can have 30 meters. Let's say I can have 30 meters, but even at 30 meters, you saw that the distance was something like 3 millimeters, right? So 3 millimeters from the beam is really, I wouldn't put my detectors 3 millimeters from the beam because they wobble the beam all the time. It'll fry them. What could I do here?
What if we put some magnetic field which will reflect?
Exactly. That's exactly right. So for Compton measurements, magnetic fields or specific dipoles are very important. So this is the EIC Compton layout. So this is the hadron beam coming in. So you can see the different magnets. In blue, you have dipoles. In red, you have quadrupoles. So you can pass it along. Do you know what the difference between, what does a dipole do to the?
Dipole are like two charges, particle force.
So do you know what it will do to the electron beam? No, you want to call a friend?
It steers it.
Yes, so it moves it around, right? So a dipole, exactly right. So it moves the beam around, right? So it moves the electron one way or another, depending on the side of the field. Do you know what a quad field does? Yeah.
Yes, quad field serves to focus the beam. It's like
In what direction?
it depends on the orientation of the magnets. It's
Very good. So a quadrupole field will focus the beam in one direction, defocus it in the other. Yeah. So what we have here is we're planning to build the Compton IP here. It'll pass through a quad that does some focusing, but the important part is this dipole, where it'll take the main electron beam will continue going on its merry way to the IP. The scattered electrons, you can pass along. What energy are the scattered electrons compared to the electron beam? Yes. So if I had a dipole here that moved, let's imagine I have, let's do that real quick. If I have my electron beam comes in and goes here. Now I have my scattered electron that is coming in here. Where is it going to go? Is it going to go on this side or that side? It'll go further, right? Because it has less energy, same power, it'll bend it more, right? So what this means is that if I have a strong enough magnetic field, I can put my detector here, far away. Now I have my photon coming in from here. We said it's backscattered. What will happen to the photon in the dipole? Nothing, exactly right. So my photon will go that way. So now I can place my photon detector safely away from the beam. Does that make sense? Yes? No? Yes. Okay. All right. So This is something that we can talk about later as well, but at the EIC, turns out that having your Compton interaction point here makes it difficult to make a measurement. Because not only is it's mostly longitudinal, but it also has some transverse angle. So exactly as we were pointing out earlier, the electron beam will have some weird angle that we need to be able to measure. So in fact, and this depends differently. So at 5 GeV, you have 97% longitudinal. At 18 GeV, you have 70% longitudinal. Yeah. So this in fact will be the most complex high precision Compton measurement ever attempted. So I won't dwell too much on this, just to point out this is different Compton measurements throughout history. And you can see that in terms of systematic uncertainties, most of these will get statistical precision, very small statistical precision. It's the systematic with which you make that measurement that will count. And you can see that, you know, as we're getting closer to the present day, measurements are going smaller and smaller in precision. And one that I've added recently, there's been a measurement of 0.5 systematic at Jefferson Lab in Halle as well. All right, so who has the thing? All right, I've been talking up the Compton, and I've said it's amazing, and but can you imagine any issues with it? All right, this is a good one. If you look at this, can you imagine any issue with the Compton just looking at this plot?
You are not counted for a small angle, very small angle.
So this is rho, and this different colors are the energy. So how is the analyzing power different at different energies?
Positive or negative?
How would you describe the red curve versus the blue curve? How would you describe the red curve versus the blue curve? It's what? Yes, exactly, right. That's exactly right. So I have a smaller analyzing power at smaller energies, actually. So if I have a smaller analyzing power and I have, what is the other thing that we talked about? The maximum photon energy decreases or increases as I decrease my beam energy. Do you remember? That's perfectly fine. Does anyone else remember what happens to my maximum photon energy if I reduce the electron beam energy? It's what? Yes, it'll be smaller. So now if first off, so two issues here. I change my energy, my analyzing power changes. So my calculations are going to be slightly different. If I have the same uncertainty in terms of my calculation for this curve and that curve, relatively, I'm doing worse here. Secondly, the energy of my backscattered photon is going to be different. So my calorimeter is going to behave differently. I might need a different system. So you can pass that along. If I have two different detection systems, how are the systematics going to be between the two of them? You think? Are they going to be the same or different? Yes, they're going to be different, right? Because it's just two. I mean, yeah, I'm not asking really hard questions. So the two different technologies will give me two different resolutions in terms of energy. And that means that I'll have different systematics. So for the EIC, where we actually have 3 different running energies, it means I'll have different systematics at different energies. So the content can be an issue. The other thing that we were pointing out at the analyzing power, at 5 GeV, the analyzing power is very small. Now, if I go to smaller energies than 1 GeV, the content is actually not that useful. Who has the doohickey? All right. How do we produce an electron beam? Yep.
Material with the laser.
Right. Once it comes out of the laser, what sort of energy does it have? Yes.
Couple of electron volts.
Yes, a couple of electron volts. Up, actually, 532 nanometers is also a couple of electron volts, something like that, right? So it'll have electron volt type energies, and then we start accelerating them. Now, if I make a measurement right before my detector here, I know it's at full energy, and I measure 0. Yeah, I have no polarization. What happened? Where's the problem? How can I tell at which point in the acceleration process I had a problem? Was the electron beam polarized at the beginning?
No.
I don't know. Maybe during the acceleration process, it got depolarized somehow. There's depolarizing resonances. So I would need to have a measurement. I need to be able to make a measurement at different energies. Yes. So particularly in the injector here, you can look at different type of technologies. So, or different types of scattering. So there's Mott scattering, and this is electron on a high Z nucleus. And this uses spin orbit coupling. And at MEV level scales, not EVs, but at MEV level scales where the injector generally lives, you can make polarization measurements. So now if I know in my injector that I'm at 80% and I get to my detector and I'm at 60%, I know in between I've lost a bunch. The other one is molar scattering, where I scattered polarized electrons off of other polarized electrons. Most of the time, these are in iron foils. So I get very pure iron foils and I polarize them using an external magnetic field. And this actually runs from MEV, where I have my Mott scattering, to GeV scales. So actually, somewhere in between the acceleration process, I could put a molar polarimeter that would be able to tell me what my polarization is. And now I can actually make measurements in between. The downside of this is that it's usually destructive. So now if I imagine putting an iron foil into a beam of electrons, what's going to happen to the electrons that are not scattered, that are not molar scattered? Who has the doohickey? You have the doohickey, right? Yeah. What's going to happen to the other electrons? Yeah, well, not molar scattered. But clearly that's not the answer I want, right? Yeah, that's right. So yeah, so what happens is there are other physics processes besides molar, right? And if you look in the PDG, you can actually calculate a multiple scattering angle, and you'll actually find that most of them will go at a particular angle. So it's not going to be a nice beam that I can then reuse and put into my detector and interact with my hadrons. So it's a destructive measurement, but you also get high rates, so you can do it fairly quickly. All right, so where, let's see, give me a second here. Actually, all right, so all right, we'll do one last thing. All right, we'll do the recap. Who you can pass the thing along? Oh, actually, no. Oh, yeah, that's right. Okay, so all right, because we're going to do exactly the same recap. So what have we learned so far? We're basically wrapping up here. So if we want to measure asymmetries, what's besides actually getting the counts, we also need to know what?
You also need to know the energy of the scattered photons.
Yep. And what else?
You should also know.
No, you can pass it along. You can do sort of like a
Lasers are great.
Sorry?
Lasers are great.
Lasers are great. We definitely learned that. Yep, that's right. Lasers are awesome. So in order to be able to measure the polarization of these electrons, which comes in your asymmetry here, we need to know a physics process, right? And we've extensively talked about the Compton. And you can have these analyzing powers that are as a function of what? Next. You don't have to pass it along. We'll just keep going. So, oh yeah, that's right. You haven't said a peep today. All right. These are as a function of what?
Rho, which is the ratio of the gamma energy to the maximum gamma energy.
Yeah, so it's basically some fractional energy. And Brenna, what's the important part about these analyzing powers?
That they don't really, they're good at higher energies, but they're not as good at lower energies.
Yeah.
That's
Yep. And in terms of form here, for me, experimentalist that hates calibrating my detectors, what's important about this?
in what sense?
In the shape of the analyzing power here. Do you remember we were talking about it
I
earlier?
was frantically trying to get my code to work, but I looked and I saw this and was like, that doesn't look right, and then was back in my code.
Okay, fair enough. Anybody else? What was important about this?
Consistency, right?
Say that again.
Consistency will look. Whether the.
I'm sorry, I
Consistency, right?
consistency, right? It's consistency, but what happens to the asymmetry here? What's the analyzing power here? It's, and here it's, so I have a zero crossing. So I know my maximum energy and I can find out a zero crossing, and that can give me an easy calibration for my energy. Now, if I have a transverse asymmetry, somebody told me that we're going to have some phi dependence, and this is what the transverse asymmetry looks like. So now if I have a transversely polarized electron, z-axis, this is the asymmetry, this is x, and this is y. So I will have positive analyzing powers on the top, negative analyzing powers on the bottom. The other couple of things that we just briefly touched on, but I'm happy to talk about either later. Question.
The heat map plot you have there of the transverse asymmetry.
Yep.
Yeah, because one's negative on one side, do they kind of act, do they act together where they'll kind of essentially double the effect you'll see?
Correct. Yes. So if you want to make this measurement, what in fact people have done, specifically at Hera, they've taken a calorimeter block and made a bunch of stacked a bunch of vertical calorimeter blocks, and they measured positive asymmetry, negative asymmetry, and so on. And they drew one curve like that. And I have it in here, but actually, let me get into that. That's a good question. Oh, here it is. All right. So if you imagine taking this and sort of averaging up everything on the y-axis, this is the vertical position. This is the asymmetry that you'll see. Again, it crosses 0 as 0 in the middle of your interaction here, but you'll have negative asymmetries one side, positive asymmetries on the others. Does that sort of answer your question? Okay. All right. So the last couple of things we touched on, and I'll be happy to answer questions about, are the Mott polarimeter. That is very interesting. The scattering, unlike the Compton, where it goes backwards. So the backward scattered photon is important. Actually similar. The electron gets bounced off something like gold, and it goes at scattering angles of something like 170 degrees. So very backward scattering angles is where you have large analyzing power. So this Sherman function you can think about as an analyzing power. The molar, the important part about the molar is that it has a well-known energy independent analyzing power. And it's relatively flat at 90 degrees scattering in center mass. All right, so I'll, with that, actually, I'll set up some questions in the discussion thread for you. But one of the things that definitely you should think about is in this equation, polarization's on the bottom. And in this equation, polarization's on the top. Why is that? Just think about it. And with that, thank you very much. I think it's time for lunch. Questions? Yeah.
Talking about going down from 60,000 with number of photons.
Yeah.
Yeah. Are we just turning the power down on the laser? How did we do that?
Yeah. Most of the time, that's what we do. We lower the power on the laser, less photons, less interactions.
So embarrassed about the question, but over here, when the scattered electron has less energy, why does it bend more?
Because it's the same magnetic field, right?
Yeah.
So it has less energy. That's just Lorentz, right? That's Lorentz equation.
I have to go back to basics. I thought.
No.
The smaller, the larger the radius of curvature.
The smaller the energy, I think the smaller the radius of curvature.
Okay.
I think no, you're fine. That's what I remember. But imagine having, how I think about it is intuitively, imagine having a kicking something, right? So if something comes in transversely with a lot of energy and I kick it, it's going to go there. If it has less energy, if I kick it, it'll go that way, right? It'll bend more. So that's what the magnet does. The magnet kicks the electrons in one direction. Less energy means that it'll bend more. Question? Yeah.
Here, you said that we are placing the electron detector like a bit far away from the beam line.
Yeah.
How far is it? Because when I see the beam magnets, I couldn't see the difference from the beam line.
Yeah, that's my drawing there was sneaky to make it look nice, but the electron detector here sits the electron detector here sits millimeters from the beam. I think something like 12 millimeters from the beam. It's not 3 millimeters, which I said will make me nervous, but 12 millimeters still makes me nervous. I'll burn some, but it is what it is.
And what about the photon detector? It is in the same beam line or?
So the photon detector, like we said, nothing happens to it, right? So it goes straight. So you can't see this because it's very zoomed in. So it's like the curvature of the Earth, it's really flat here, but I promise you the electron bends. So the photon doesn't bend and it keeps going that way and it reaches to the side of this quad, which is I think 30 meters away from the interaction point, and it's actually significantly away in the sense that it's outside of the beam pipe. I don't have to have it in the beam pipe. While the electron here, I actually have to put the detector inside the beam pipe where the vacuum is with all the other electrons. Does that make sense? Yep.
Straddling of the beam concern for the photon detector because we are bending the beam in front of it.
The synchrotron radiation is a big concern for the detectors, and in fact, it's one of those things that we're calculating now. Make sure that the background that comes in for the photon detector doesn't mess up and ruin the analyzing power. But it's a great question. Yes, it is a big concern.
I've seen this thing.
Yep. Great question. Anybody up?
Kicks. I got some help from a friend, but last week we saw these beautiful animations, right, of the things coming in and that they go.
Yeah.
Did we cover that?
No. So that happens here. So this, you can barely see it here. The crab cavity magnet is sitting right here. So what our interaction is much simple. The electron goes on straight. We have a photon as a slight angle, a laser coming in at a slight angle and all that. And in fact, because of the crab cavity, because you have to give some kick, there's going to be some spin precession. And that's why in order to get 100% longitudinally polarized at the IP, they need to keep it some transverse polarization here. So much so that at 18 GeV in this location, it's half longitudinal, half horizontal. No, horizontal. Yeah, I think so. Yeah. Any other questions? All right. Thank you very much.
As returned from lunch, it's all +1.
Right. Thank you. That was a bit much.
Oh, that's okay.
I will be conservative today, and then
Yeah.
maybe that should say. I'm thinking about it because it's really weird. I might say.
Magic eraser works, yeah. I like that.
Yeah, right.
Yes, I'll put my backpack in the.
Spam for parking.
If I ask boss Robbie.
Yeah, I was about to do that.
Oh, okay.
Yeah, you have a card from.
Oh, I have to go. I have to go there. She said she was preparing a card.
Okay.
So I'll go to her, ask Bobby if he wants to join, and then.
Oh, he's gonna join you.
Yeah.
All right.
Hey, oh yeah, we're Target.
Oh, God.
Fancy, yeah.
That's where I get my.
I'm a fancy man.